All right, we've all been there. You write a Python script, you hit run, and like magic, it just works. But have you ever really stopped and wondered what's happening in that split second? What's the secret sauce that turns your beautiful human-readable code into something a computer can actually understand? Well, in this explainer, we're going to pull back that curtain. This brings us to one of the biggest, most classic questions in the Python world. It's a question that trips up beginners and veterans alike. Is Python a compiled language, like C++ or Java, where everything gets translated to machine code up front? Or is it an interpreted language, like a shell script, that gets read and executed line by line?
And the answer, which might surprise you, is kind of a trick question. It's both. Python uses this really clever hybrid model, a two-stage process that combines the best of compilation and interpretation. Here's the key thing to remember. Python first compiles your source code, but not into machine code. It compiles it into something else entirely. Let's break that down.
Okay, let's dive into that first stage, the compiler. I want you to think of the Python compiler as an architect. It takes your high-level design, your .py script, and translates it into a super detailed, highly structured blueprint that a builder can easily follow.
You see, the code that we write, with all its friendly words like def, for, and import, is perfect for us humans to read. But to the Python runtime engine, it's really just a text file. So the very first step is to transform this text into a much more organized and efficient format that it can actually work with.
And this translation happens in 4 key steps. First, your code gets broken down into tokens. These are the smallest units of meaning, like the keyword def or a variable name. Think of them as individual words. Next, these tokens are arranged into a parse tree, which is basically a map of your code's grammar, like a sentence diagram from school. From there, the tree is refined into what's called an abstract syntax tree, or AST, which captures the logical meaning of your code. And finally, this AST is used to generate the star of our show, bytecode. Each step gets us a little further from human text and a little closer to machine instructions.
So I've been throwing this word bytecode around, but what in the world does it actually look like? Well, this is it. This is the architect's blueprint. It's the output of the compiler, and it's the native language that Python's interpreter speaks.
Let's start with a function we all know and love, super simple, called add. It takes 2 arguments, x and y, and it returns their sum. You can't get much simpler than this, right? This is our human-readable code. So, what does the compiler turn this into?
And there it is. This is the bytecode for our add function. It might look a little strange, but it's just a series of simple, platform-independent instructions. You can almost read it like a recipe. First, load fast says grab the first local variable, x. Then grab the second one, y. Binary add, well, that's pretty self-explanatory. And finally, return value tells it to return whatever is on top of the stack. Simple, step by step.
Now, this bytecode doesn't just float around on its own. It's neatly packaged into something called a code object. You can think of a code object as a folder that holds the blueprint. It doesn't just contain the bytecode instructions, it also holds other vital info, like the names of your local variables and any constants your function might use.
Okay, so our architect has drawn up the plans and put them in a folder. Now it's time to actually build something. This is where our second major player comes onto the scene, the interpreter. And if the compiler is the architect, you can think of the interpreter as the master builder who reads that blueprint.
This master builder is the Python virtual machine, or PVM for short. This is the absolute core runtime engine of Python. Its job is incredibly important, but it's also conceptually pretty simple. It takes the bytecode we just looked at, reads one instruction at a time, and executes it. This is the interpretation part of Python's whole process.
So how does the PVM keep track of what it's doing? Well, for every single function call, it creates a frame object. If the code object is the blueprint, the frame object is the builder's workspace for that specific task. It holds the current values of local variables, like what x and y are equal to right now, and it has an instruction pointer that tells the PVM which line of bytecode it needs to execute next. So we have our architect, the compiler, and our builder, the interpreter. So why does Python do this? Why not just pick one? Let's bring it all together and see exactly why this hybrid approach is so darn powerful.
So this table really lays out the fundamental trade-offs. A pure compiler is generally way faster because all that heavy lifting of translation happens before you even run the program. But it uses more memory up front and the final result isn't portable. You have to recompile it for every different type of machine. An interpreter, on the other hand, is super portable and memory efficient, but it can be slower because it's translating on the fly.
And this is exactly how Python gets the best of both worlds. That initial compilation to bytecode is a one-time performance optimization. It's much, much faster for the PVM to execute that simple bytecode than it is to reparse your original source code every single time. And because that bytecode is generic, it can run on any machine in the world as long as it has a Python virtual machine installed, which gives us that incredible portability we all love.
This brings us to something you've probably seen in your own projects, those little .pyc files. That's it. That's the result of the compilation stage. When you import a module, Python is smart. It compiles it to bytecode and saves it as a .pyc file. So the next time you run your program, Python can just grab this pre-compiled blueprint directly, skipping the whole compilation step and making your program start up a lot faster.
So we've seen how Python's unique dance of compilation and interpretation gives it both speed and flexibility. But this whole system, this PVM executing bytecode one instruction at a time, has some really profound implications. Which leads me to a final, thought-provoking question. How does this very model lead to one of Python's most talked about and sometimes debated features, the global interpreter lock? Well, that's a story for another explainer.